Let's take a look at enols and enolates. Under catalytic acid or catalytic base, this ketone can tautomerize to form an enol. And there are two versions that we could form. We could put the alkene on the other side as well. So this is catalytic acid or base. And normally the ratio is 99:1. There's a lot more ketone than there is enol. And there are ways to improve the amount of enol. But remember, with Le Chatelier's principle, as long as there's a little bit of enol, we could use that in a reaction, and Le Chatelier's principle will affect this equilibrium and produce more enol for us. So let's look at the mechanisms for both of these. Let's look at the acid catalyzed mechanism first. Just take our generic ketone, we'll use acetone in this case, and let's say I'm doing this in sulfuric acid, maybe in water solvent, maybe not. But the first step, as we've talked about in class, whenever you're faced with an acid catalyst, protonate something. And the oxygen on the ketone is a good thing to protonate in this case. As we saw in the ketones and aldehydes chapter, that makes this a better electrophile. We could then take water, remove the alpha hydrogen from the ketone, the protonated ketone, and we end up with this molecule. And this is the enol. And the enol has a resonance form that would look like this. This is not a very highly contributing form because, as you see, there are separated charges, and we have no charges on the other resonance form. But nonetheless, this form does give us some insight into the reactivity of the enol. We know that the enol is nucleophilic at this carbon, or this carbon, right? The same thing, because of that resonance form. Before I go further, I want to briefly mention we're going to use a lot of alpha carbons labeling in this chapter. And so if we look at the ketone up here, there are several carbons next to the ketone, and we're going to label the alpha carbons as those that are not the carbonyl carbon, but right next to the carbonyl carbon. And then we also have beta carbons and gamma carbons, if you remember your Greek alphabet, I think. I'm actually not sure if that gamma is upside down or not. I'll let you figure that out. But that is a kind of how we're going to label carbons. The alpha carbon will be very important in this chapter. We'll see a little bit of beta carbon labeling as well. Gamma is probably not at all. So when we talk about alpha carbons, we are talking about the carbons that are next to the ketone or aldehyde, directly attached to the ketone or aldehyde, not the carbonyl carbon, which would be called the carbonyl carbon. Okay, let's go and look at the base catalyzed enol formation now. Let's start with acetone again. I'm going to use base in water, and the alpha carbon is reasonably acidic, and we'll see why right now. So I'm going to remove the alpha hydrogen. I'm going to make a lone pair and a negative charge at that position, and I can draw some resonance, much like the resonance of the enol that I showed earlier, showing why that position is reasonably acidic. And so now you can see that here I have my two resonance structures. This is called an enolate because it is an anion. Compare that with enol up here, which is a neutral species. And so my enolate can have a negative charge on the carbon or on the oxygen, which means it can be nucleophilic at the carbon or at the oxygen. And as we will see in this chapter, most of the time it is nucleophilic at the carbon. So if we wanted to react this with, say, ethyl chloride, most likely the ethyl group would be added to this alpha carbon. So we're not done with our enol formation yet, so let's continue with that. We want to make the neutral enol, so we're going to take a hydrogen from water and draw this proton transfer. It's not what I wanted, actually. Let's erase that. I'm going to draw the arrow from the O minus, and that's going to give me the enol, which was my goal in this case. But you can see how I might take the enolate and protonate either the O or the C. The C gives me back to the ketone. Protonating the O gives me an enol. And so this resonance structure, again, is the reason that we have slightly acidic alpha hydrogens. One more thing we want to point out. We are going to look at alpha hydrogens of aldehydes as well. So here are the alpha hydrogens. This is the aldehyde hydrogen. It is not acidic. Do not remove the do not remove the aldehyde hydrogen. It has much different acidity than these alpha hydrogens. So these hydrogens are acidic. This is not acidic. Remove these with base. Do not remove this one with a base. So now, what base would we use to affect these deprotonations? Well, let's refresh our memory from chapter 3. What if we used acetone and ethoxide? We're going to find that the equilibrium lies far to the left. How do we know that? Well, we can look at the pKa's of the acids. And you can find these in chapter 3 or inside your textbook. I think the front cover might have that. And so you can see that the pKa difference here is over 3 orders of magnitude, which is over 1,000-fold. So if we were going to figure out what the ratio of starting material to products are, we might say at least 1,000 to 1. And you could do the math to come up with a more accurate number, but you can see that if we mix ethoxide with acetone, we're not going to get a whole lot of enolate. And that doesn't mean we can't use the enolate in a reaction. That just means we have more acetone and ethoxide. And if you look at it, ethoxide is a pretty good nucleophile as well. It may actually compete with our enolate to be a nucleophile if we're trying to use this carbon as a nucleophile. So this setup here may not be the best way to go if our goal is to use the alpha carbon as a nucleophile, because we'll also have a lot of this ethoxide present as a nucleophile. So how can we use a stronger base maybe to avoid this problem? And we want to design an irreversible reaction now. I'm going to use the same acetone. I'm going to use an amide base now, which is a nitrogen that has lost a hydrogen and has 2 lone pairs and a negative charge. This is the outcome I would expect. And again, pKa's, we can look those up. Nitrogens or ammonias, amines, typically have pKa's around 36. And we already saw the pK of acetone is 19.2. Now you can do the math. This is nearly 17 orders of magnitude difference. And anytime we're at 10 or more orders of magnitude, we basically call it irreversible. What does that mean? That means if I mix 1 equivalent of acetone, 1 equivalent of amide, I have 0 amides or acetones left. I just have these 2 species left at equilibrium. And so this is often called LDA because there's often a lithium cation there. So this is a non-nucleophilic base. And let me fix that. We could also look at some hydrogens that are more acidic than those on acetone. What if we have a hydrogen that is between 2 carbonyls? And again, you can look this hydrogen up in your pKa table as well. And in this case, we have double resonance stabilization. We could stabilize that negative charge via either of the carbonyls. And so if I look at the pKa differences here, I have a pK of about 9 for that doubly alpha hydrogen, and I have a pK of about 15.9 for the ethanol. And so that's about 7 orders of magnitude difference, which means I would expect 1 to basically a million, which on the grand scheme of things isn't a whole lot, but you can see how we're able to use ethanol to basically eliminate all of those hydrogens, use up all of the ethoxide. I'm sorry, I said ethanol, I meant ethoxide. We could use all of the ethoxide up, all of this hydrogen up, pretty much come up with 100% of the products here, and that would allow us to use then this carbon as a nucleophile in subsequent reactions. So depending on what type of hydrogen we're looking at, we can choose the appropriate base to ensure that we have the maximum amount of deprotonated alpha carbon.